Okay, any questions? Yes? The torque acting on a circuit. So let's see. We have a region of space where we have a magnetic field. Let's say, just for simplicity, assume a uniform magnetic field. Then we assume that we put some loop in it. Well, the loop can have an arbitrary shape, but again, just for simplicity, we assume that we put a rectangular loop. So it just have such a shape. This side is this one and this one. This is the bottom side, this is the top side. So it's just like we have the rectangle, the magnetic field is uniform in that direction. We just put it like this. So you just see it from the side. Then of course, since we have a magnetic field and the current carrying loop, so it just circulates like this. At the top wire is coming towards you, at the bottom wire is going away from you. We have this loop, it carries current in a magnetic field, so there will be forces acting on it. And if you remember the expression of the force, dF, this is the force acting on a very small segment of a wire that is carrying a current I, and that has a length dl. This is the force acting on a very small segment of the wire. Now, if B is uniform, then the force, the total force will be just I times L cross B. L is just a vector along the wire. It's a uniform and straight wire. It's along the wire, and I is just the current. So let's come here. Let's just assume that this is the direction of the current from this side view. Now the top part. Okay, this is the top. The current is coming in that direction. The magnetic field is in that direction. So what is the direction of the force acting on the top part? This is the direction of L. This is the direction of B. So it's just upwards. What is the angle between I and B? 90 degrees. So the magnitude of the force acting on the top, this is F top. And the magnitude of this force is equal to I times L, let's call this length L, this length A, I, L times B. Now let's look at the bottom. At the bottom, this is the direction of the current. B is still in that direction. So this is L vector, this is B. So it's downward. So the force acting on the bottom is pointing downward. And the magnitude of the force acting at the bottom is also I times L times B. So they have equal magnitudes and opposite directions, this force and this force. Now let's look at this, the force acting on this side. On the side looking closer to you, the current is going down in this direction. This is the direction of the current. This is the direction of B. So what is the direction of the force? Towards you. So this is the force acting on one side. Towards you. What about the other side? You see the magnetic field on the top is coming towards you, so it's going down. On this side, it is going up. So this is the direction of L. B is again in that direction, so the force is L cross B inside. This is the other force. So you see there is a force acting on this side. which is pointing in that direction. There is a force acting on this side, which is in the opposite direction. Well, these two forces, they just pass through the same points, so they don't create any torque, they don't create any net force. But if you look at the force acting on the top, it is in that direction, and acting at this point, so it is passing along this line. The force at this side is pointing downward, it is acting on this plane, let's say. So these two forces, they have the same magnitude, so they cancel each other, there is no net force, but they create a net torque around the, let's say, the center of mass of this loop. So they will try to rotate this loop. They will create a torque. Now we can calculate the torque. Let's say the torque, the general definition of the torque is just if there are many forces acting on my system, R cross Ri cross Fi, this is the definition of the torque. So you just calculate the torque created by each one of the forces, taking into account the point that they are acting, this Ri over there, and just sum them up. Now let's look at this top force. And let's try to calculate the torque relative to this point A. Now, relative to that point A, the force is acting at the top. Okay, so this is my point A. The force is acting over here. It is pointing upward. R is in that direction, from here to that point. Force is in that direction. What is the direction of the torque? Inside. Now let's look at the other one. The force is downward. R is in that direction. The torque, RF, is inside. So both of them create a torque into the screen. The torque acting on this system will be into the screen. Now the torque created by the top force, in fact, will be equal to the torque created by the bottom force. And their magnitude well, the magnitude of the torque is just the distances. Well, the distance is A over 2. So since we are calculating the torque relative to the center, so the distance at which the force acts is A over 2 away, times the force. The force has a magnitude I times L times B. And what about the angle between the two? Let's just say, so here, let's call that angle theta. So we have, this is R, this is F. The angle between the two is just this theta. We have sine theta. Or we can write this as I times A times L over 2 B times sine theta. So the total torque is equal to the torque created by the top force, the torque created by the bottom force. They are equal in the same direction. They have the equal magnitude. It's twice the torque created by the bottom force, let's say. And so the magnitude of the torque is equal to I times A times L times B times sine theta. Now this combination, we define it to be mu. It's just a name for the time being. Then the torque, the magnitude of the torque is mu times B times sine theta. Now if you look at this one, B is the magnitude of some vector. And then we have multiplied by sine theta. It just looks like the cross product. The only missing piece is that mu should be a vector if we are to write this as a cross product. So we have to define a mu vector so that the torque will be equal to mu cross B. Now let's come here. If we define the mu vector to be pointing in this direction, Then this angle over here is nothing but theta. This is nothing but B. And what is the direction of B cross mu? Into the screen, just in the direction of the torque. So if we write torque is equal to B cross mu, if we did everything correct, then B cross mu has the same magnitude as the torque, and it has the same direction as the torque. Now, the direction of the torque, we had misidentified it. You see, the torque, let's consider this force. This is R, this is F. No. This is R, this is F. R cross F is towards you, not away from you. So the direction of the torque is out of the screen. So the torque is mu cross B. This is the correct expression. So what does it do? Let's see, the forces. We have this one. No, this is the shape of our loop. This is the direction of the magnetic field. The magnetic dipole moment is pointing in this direction. The torque is such that it's trying to rotate it like this, right? So that this is B, this is mu, this is B. So the torque is just try to rotate the mu in the direction of B. If it was like this, then again the torque would just try to rotate mu in the direction of the B. So the torque is always such that it will try to align the magnetic moment with the magnetic field. The magnetic moment will be aligning with the magnetic field. Now, this is the conventional definition. How we chose it to be, why did we choose it to be in this direction? It is basically what we use is the right-hand rule again. Just curl your fingers in the direction of the current, then your thumb gives you the direction of the magnetic dipole moment. Now we can also write this expression of the magnetic dipole moment vector. This is equal to I times the area vector. So the magnetic dipole vector is in the direction of the area vector. So what are you doing? Are you translating it around? If under translation, there's no work done. So the work is 0. If you try to rotate it, you see, there won't be any torque if the magnetic moment and the magnetic field, they are in the same direction. If you want to rotate it, you have to exert a force. So you are doing some work. You have to do some work to rotate it. So you are doing some work, and which will be converted into stored potential energy. No, it's not the magnetic field, it's you are doing work.
Well, I just placed it that way, I wrote magnetic field, it's up to magnetic field. Well, I just put it that way, okay? But the magnetic field has the angle with the normal of the loop, so then you create a force, then
Okay.
which will create the torque.
Okay, which will do a work.
Yeah, which will do the work.
True.
I just rotated, put it that way, I didn't do anything. So it will just keep.
But rotating does work. You see, if you want to rotate this, you have to exert a force over here. And that force you are pushing it. So that force, there is a displacement of the point that you are exerting the force, and hence you are doing work if you want to rotate it.
Well, I will not rotate it.
Okay.
The
Okay, so that, if you just put it in a magnetic field just like this, it will rotate it, and hence there will be a kinetic energy. It will gain kinetic energy.
So there is work.
There is work done by the magnetic field. There is. Then you will ask, oh, we said that magnetic field doesn't do any work. So what's going on? How come? Yeah, I will leave it at that for you to think about it. I will not go into that discussion anymore. Magnetic field doesn't do any work on the charges. But if you talk about average work done when you are moving many, many charges, then in a conductor, then you end up having some work, which seems to be done by the magnetic field. Yes?
Can we go into the derived energy equations?
These?
Potential energy equations.
From this one. Why?
Because there was a question.
Yeah, I mean, that was a question for asking you to review mechanics. Because if you remember in mechanics, we had shown that the work done by a torque is equal to torque d theta.
So that's it.
That's it.
Another question.
And this just becomes, the torque is proportional to sine theta d theta. If you integrate it, it becomes proportional to cosine theta. So the work done is proportional to, or the potential energy is equal to minus mu dot B.
Okay, I have another question, which was in this homework, latest book, which was the first question last B. We asked a lot of questions. Okay, I'm done. It was a loop, a square loop, which length L was the current I. And the last part was one of the wires was on the x-axis, the other one was on the y-axis. And one of the y-axis was applying auxiliary torque on this one. Asking that, and what was asked was that torque, and I couldn't do it. I did it, but actually I went to a few assistants for that as well, and I didn't get any done. That's why I'm asking.
Well, let's see. So we have such a current carrying loop, right? Let's look at this one. What is the magnetic field that it creates at this point? What is the direction? Outside. So this wire will create a magnetic field pointing outside on this side. So there is a magnetic field created along this wire due to the other wires. And this wire is carrying a current. So what is the force what is the direction of the force acting on this one? Right? So there is a force. Well, if you just calculate the torque with respect to, let's say, this point, it creates a torque. Well, how do you calculate it? Well, that will involve many integrals. First of all, you have to calculate the magnetic field created by such a finite length wire. And then, of course, then you create this magnetic field along this line. And then magnetic field will be changing. So at each small segment that you are exerting your torque, you have to sum them up. So I will not do that.
I got the point when you said it involves many integrals. Okay.
You see, homeworks are places where I mean, in the homework questions, I usually try to arrange some simple questions, which most of you should solve, and some very tough ones, which might involve many integrals, which maybe one of you will solve. Other questions? Let us imagine something else. Let us imagine we have a loop. And we have, let's say, we somehow build this current. There's a current running in the loop. And then we take two magnets. So these magnets are just, they continue. This is, let's say, the North Pole. This is the South Pole. They are big enough so we can just say that it is more or less uniform, the magnetic field lines in between. And then we move these magnets. It just continues. And we move these magnets to the place where we have this current. So there will be an additional EMF created. Let's say this loop has some magnetic dipole moment already because there is a current. What's the direction of the magnetic dipole moment? It's in the upward direction. Then we bring this magnet. So will the magnetic dipole moment increase or decrease? Why? So? So what is negative, what is positive? What are your conventions? Well, let's do the lens rule. Okay? So what happens when we bring this magnet is that we are creating an flux in the downward direction, right? When we move this magnet, or when we bring this circuit inside our magnet, we are basically creating a flux in the downward direction in our material, in our loop. But lens rule tells me that the induced current or the induced EMF will be such that it will try to resist the change that creates it. So since the reason there will be an induced EMF is that the flux has increased in the downward sense, depending on your convention, you can say that it's positive or negative. It increased in the downward sense. The current will try to increase it in the upward sense, so that the net flux, the net increase in the flux will be reduced. But that means the current should get larger. So I will end up having a larger current when I move this, either when I move my my loop into the magnets, or when I move the magnets into my material. Agree? So mu the magnitude of mu increases in the given direction. Well, in fact, what happens if we flip the polarity of the magnets? The South Pole is above, the North Pole is below. It will decrease. So in both cases, in fact, the magnetic dipole moment will change, and the change in the magnetic dipole moment will be in the opposite direction to the magnetic field, in both of them. Are you following? Okay. So let's take a material, an arbitrary material. It's made up of atoms, which are nothing but we have the nuclei, and around the nuclei we have electrons. Okay, the orbits of the electrons are not just trajectories in the classical sense, but they form this electron cloud, let's say. Now, we have the electrons are nothing but on the average moving charges. Well, moving charges, we can just, on the average, we can treat them as circular currents. Do you agree? There are many electrons in an atom, and the electrons themselves have also their own magnetic dipole moment, the electrons, plus they are orbiting the nuclei, and hence this, due to this orbital motion, they have an additional magnetic dipole moment. So since we have many electrons in the atom, they are just rotating on the average in various directions. And when you sum them up, you might have a non-zero magnetic dipole moment or a finite magnetic dipole moment. A zero or a non-zero magnetic dipole moment. It depends on the materials. Let's just assume that every atom, let's just assume the atoms have a net magnetic dipole moment. This is our assumption. We pick up a material which has the atoms making the material, or the molecules making our material, they have a magnetic dipole moment which is non-zero. And now we put this in a magnetic field. So our material is just a collection of magnetic dipoles. Well, you can treat the electrons as small charge rotating spheres. They're rotating. Don't repeat this in the quantum physics course. Okay? That's a wrong description, but at least in the case of understanding the magnetic dipole moments of the electrons, it works to the limit. So we have this material. What happens if we put it in an external magnetic field? This material is made up of small magnetic dipoles. And we had just said that magnetic dipoles, if we put them in a magnetic field, they will feel a torque. And the torque will be such that the magnetic dipoles will align in the direction of the magnetic moment. Agree? So we will have, more or less, this will be the orientation of the magnetic dipoles in the material. Well, they will not be exactly aligned due to various effects, but on the average, they will be aligned. Now, these magnetic dipoles, each one of them creates a magnetic field along the dipole. We had seen that if you have a magnetic dipole, it creates, this is a mu, it creates a magnetic field like this. At least in this region, close to the magnetic dipole, it creates magnetic field lines in the direction of the magnetic dipole. Are you following? So basically, the whole thing becomes magnetized to some level. Inside, there is the magnetic field created by the external magnetic, whatever creates the external magnetic field, plus there is the magnetic field created by these dipoles. So the total inside will be the magnetic field, the external magnetic field, plus the magnetic field of the dipoles, which they are both pointing in the same direction, which basically tells us that the magnetic field inside, the total magnetic field inside, will be larger than the external magnetic field in magnitude. Well, this is kind of contrary to what we had in electric fields. If you remember our discussion of dielectrics, we said that if you put a material, an insulator, in an electric field, the electrons just move in opposite directions such that the electric field inside our dielectric will be smaller than the applied electric field, because there will be two contributions in opposite directions. In the case of the magnetic properties, if you put a material in a magnetic field, if this material has atoms or molecules making this material have a magnetic dipole moment, the magnetic field inside will be larger than the external magnetic field. Such materials are what we call paramagnetic materials. This is one of the phenomena that will appear if you put a matter in a region where there is a magnetic field. So since the magnetic dipoles in your material will be aligned in the direction of the magnetic field, there will be a larger magnetic field inside.
Does it mean that these materials without the external magnetic field, they don't have any magnetic properties, but inside the magnetic field they behave like magnets?
No, their so-called magnetization without an external magnetic field is zero. With an external magnetic field, they will be magnetized. They will have non-zero magnetization. For example, iron is not such a material. But this book probably is paramagnetic. We will see what iron is. Now, this is one phenomenon. It's the alignment of the magnetic dipoles in the direction of the magnetic field. But now you see here we had discussed another phenomenon. We said that, well, if we have an object that has a magnetic field, magnetic dipole, this magnetic dipole changes in the opposite direction to the magnetic field. That is what we said, right? So the change in this magnetic material, so there will be an additional, let's say, there will be an additional magnetic dipole in the opposite direction to the magnetic field. So here we see, in fact, there will be two phenomena. One of them will be the magnetic dipoles will be aligned in the direction of the magnetic field. So because of the torque acting on the magnetic dipole. Well, the other phenomena will be that the magnetic dipoles will get smaller, or they will acquire a component in the opposite direction because of the previous phenomena. And that is called diamagnetism. Let me write it over here. Now, in any material, we will see both of these effects. If they are in the magnetic dipoles, they will be aligned in the magnetic field, but at the same time, because of the torque acting on a dipole due to a magnetic field, but we will also see this phenomena, which just means that all the magnetic dipoles will change, and the change will be in the opposite direction of the magnetic field. Now, this second phenomena, diamagnetism, is seen especially if the magnetic dipole moment of the molecules making the material have a zero net magnetic dipole moment. Well, all the electrons will contribute to the magnetic dipole moment of the electron or the molecule making our material. It might happen that they cancel each other. So there is nothing to align with the magnetic field. But nevertheless, the previous phenomena, this phenomena tells me that the magnetic dipoles of each one of the electrons will acquire an additional contribution opposite to the direction of the magnetic field. But this means that if you take this material, put it in a magnetic field, you are creating magnetic dipoles. They do not exist before. There is nothing to align. But since you are putting it in a magnetic field, you are creating additional magnetic dipoles, but they are in the opposite direction. So the magnetic field inside will be less than the external applied magnetic field. Now, if you plot the magnetic field lines, so this is a diamagnet, this is a paramagnet, so what happens if you put them in a magnetic field is this acquires a magnetic dipole moment in the opposite direction to the external magnetic field, whereas a paramagnet acquires a magnetic field in the same direction as the applied magnetic field. So if you draw the magnetic field lines, they will just go around the diamagnet. Well, not all of them. This will be how the magnetic field lines will look like. And in the case of a paramagnet, this is how they will look like. The total magnetic field lines.
Can you give examples of them? I mean, these good paramagnetic.
Well, most of the materials are paramagnetic. Most.
Conductors?
Included. I mean, there are just a few diamagnetic materials. I don't remember a specific example now. Then there's the additional phenomenon of a ferromagnet. This is a ferromagnet. And that is basically why when you put this one, it enhances the magnetic field drastically. I mean, you see, without this ferromagnet, the change is very small. I mean, you see, in these examples, in paramagnetism and diamagnetism, the change in the magnetic field is just like 1% or even less. But when you put a ferromagnet, you will see all this change. Now, the reason for this ferromagnetic material is that they are weird materials. I mean, there are just 5 elements that have this ferromagnetic property. And the property is that each electron, we said that they behave like a magnetic dipole. In these magnetic materials, the electrons, they influence each other in such a way that they try to align their magnetic dipole moments in the same direction, neighboring electrons. Without any influence, any external influence, each one of those electrons, they want to be pointing in the same direction. So what you end up having, if you look at the iron, if you could just put some iron dust on it and look at it in a microscope, you will see that iron dust will align itself in very small regions. You will see a very small region, somewhere like this, in which the magnetic dipoles will all be aligned in this direction. There will be a neighboring region which will have its magnetic dipoles aligned all in this direction. And another region over here, which will be aligned, let's say, in this direction, which contains many atoms, not just one, but many of them. And each one of these are what we call domains. If you align these domains, for example, by applying an external magnetic field, let's say this is, well, this is the external magnetic field. This is the total magnetic field, let's say. If you apply an external magnetic field, the total magnetic field, the magnitude, kind of the magnitude, increases very fast, until all the domains are in the same direction. But then something funny happens. You see, the external magnetic field will try to rotate each one of these domains in the same direction.
I think it's a wrong illustration. Go this same slope. For instance,
No, it doesn't go with the same slope. Eventually, you see, all the magnetic dipoles will be aligned with the external magnetic field. So after that point, this is, let's say, the magnetic field of the dipoles. And then suppose if you lower the external magnetic field, and when the external magnetic field goes to 0, the magnetic field created by this ferromagnetic material, it doesn't go back to 0. So it has still a net magnetic field. And the reason is, the external magnetic field just rotated these dipoles in its direction. But when you remove this external magnetic field, there is no reason why they would like to go back, because they are just sticking together. They all want to be in the same direction, so they just stay in the same direction. And if you would apply a magnetic field in the opposite direction, you have to apply some non-zero magnetic field in the opposite direction to set this magnetization of the material to 0. If you keep increasing the magnitude of the external magnetic field, it goes back. So basically, this will be its shape. So they have this weird property that their magnetization, let's call this their magnetization, doesn't depend only on the external magnetic field, but it also depends on the history of the material. So if you can have an external magnetic field, let's say at this value, and the total magnetization can be this one, or this one. It can have any one of these values. And what will determine which one it chooses will be its history. How did we reach this external magnetic field? Did we start from 0 with 0 magnetization and reach this external magnetic field? Or did we start from 0, reach some maximum value, and then lowered our magnetic field to this value? Or did we just make all this process go increase, decrease, opposite direction, increase, etc., and come back over here? So the magnetization will depend on the history. So this is called the hysteresis. Now, in this case, the magnitudes the induced magnetization, the ratio of the magnitude of the induced magnetization to the external magnetization can be of the order of 10 to the power 4 or so. So that's a huge number. So that is why, in this case, we are creating some magnetic field, some external magnetic field by this solenoid over here. When we put this ferromagnetic material, the dipoles, the domains in this ferromagnetic material enhance the applied magnetic field by orders of magnitude. So that's why we obtain such a large enhancement on this effect. So you see, if in this one, the height is something like this. If you put the ferromagnet, it reaches some distance like this. So what is the increase? Something like 5, no, even more. No, we started with this one to 5 to 6, let's say. It can reach a height of 5 to 6. So that is an increase in the potential energy of 5 to 6. Increase in the kinetic energy by a factor of 5 to 6. So the velocity basically that it acquires in this distance is almost twice or tripled by the insertion of this one. It's not just a small effect, it can be a huge effect.
Is this similar to the railgun? The way the projectile shot out, is it similar to how a railgun operates, or is this purely because of propulsion?
It is similar to the railgun in the sense that the current induced in this one is wide fields of force. Well, in the railgun, we are just pumping in the current with a constant magnetic field. So that is why it jumps. There is a magnetic force acting on this one. So both of them is based on the principle of the magnetic force. In the railgun, we are providing the current with a constant magnetic field, almost a constant one. In this one, we are inducing a current due to this changing magnetic field. Now, you can ask it later on. The exam day places will be the same. The exam hour is the same. So we will be all in this building at 1:30. It will be 3 hours, so the style of the exam will be more or less similar. So see you on Saturday.